Okay, we'll take up the topic optics, and in optics we study about light. This will be the flow of this topic. Firstly, I will tell about the general nature of light, followed by what happens when light strikes a surface separating the two mediums. And then we shall confine ourselves to reflection, and in reflection also reflection from spherical mirrors. That will be covered in first topic of optics, that will be ray optics, and another topic will be wave optics, in which we will study about the wave nature of light. So light is a wave. In detail we will study about this nature in the next topic, but just to give you introduction about it, wave, we know how energy is transferred from one point to another. If I take 2 points and we want to transfer some energy from here to here, one way is I throw a stone. In this case, stone is moving from here to here, it has kinetic energy, so it carries kinetic energy with it. But another case may be that one person is standing here and talking to the other person is standing here. In this case too, energy is being transferred, but there is no transfer of materialistic particles here. So it is transferred through the vibrations in the air, that is called wave. So wave carries energy with it, but there is no transfer of any particle when we are talking about the wave. Coming specifically to light wave, it is an electromagnetic wave. Electromagnetic wave means we have electric field, we have magnetic field, and they vibrate perpendicular to the direction of propagation. It's an electromagnetic wave. So if the light wave is in this direction, electric and magnetic fields, they will be in this plane, perpendicular to this. So if I take this as x, y and z axis, so yz plane, electric and magnetic field, they will be confined to yz plane. Both will always be perpendicular, so all three will be mutually perpendicular. That's why we call it a transverse wave. So light is a transverse wave. It's an electromagnetic wave, and it is also non-mechanical in nature. Non-mechanical means it doesn't require any medium for propagation. And that we know. How are we getting energy from sun? It's coming through vacuum. So no materialistic medium is needed for the propagation of light waves. Anyway, in this particular topic, we will talk about light ray optics. Okay, light ray is a straight line or maybe curved too. A straight line with an arrow. This is a geometrical representation actually. This tells that the energy is being transferred in this particular direction. So it's a way to represent the propagation of light wave. We use a straight line and then put an arrow over it. When this gets curved, we will do after doing the refraction. In this particular topic, we will study about reflections and refraction. Reflection basics you already are aware of, you have done in class 10th and even in classes 6th and 7th you have studied about the reflection. But anyway, if I take two mediums, air and water, say for example, and light, again I am using a ray to represent light. It strikes this surface. Now three things may happen. The light ray may bounce back, it may be absorbed by the medium, water here, or it may pass through. Bouncing back, absorption, or simply transmission. So accordingly we call it, bouncing back of light is called reflection of light. And when it is passing through, we call it refraction. And the third is absorption. So reflection is bouncing back of light from any surface. It strikes this and returns to the same medium. Now, whether it will be reflected or refracted or absorbed, it will depend on the medium. We can make surfaces which have maximum reflection or maximum refraction or even for absorption. The percentage may vary, and depending on the application, we will have mirrors or lenses or any other medium which can absorb light. Now, whenever light is striking a surface, now we shall be confining ourselves to reflection part only. Let me take 2 or 3 parallel light rays. Or the reflection may be like this or it may be like this, though in both the cases it is following the same laws that I will tell you how. But when we have parallel rays of light, we have a light beam and going in a specific direction, we call it regular reflection. And this one will be irregular reflection. Regular reflection, when a parallel light rays, group of parallel light rays, and is reflected in the same way. The reflected rays are also parallel and the incident one also parallel. So this one will be regular reflection. This is irregular reflection. In this particular case, if we are standing here, we will see our own image or even the source of light. But in this case, this surface will be visible to us. Okay, we will see only this surface. Source of light will not be visible. We cannot see our own image in this type of surface. This is optically plane surface. Optically plane. This is not optically plane. So, though both of them appear to be plane, but this type of surfaces we call them optically plane, which cause regular reflection. This is not optically plane. And reflection is very important in daily life because we see the objects because of reflection only. Light falls on the objects, it is reflected, it reaches our eye, and then we are able to see the objects. So all objects are visible to us only when light is falling on them, it is reflected and reaching our eyes. It follows a specific laws. Light is not reflected randomly in all directions. And to get this regular reflection, we need optically plane surface. So a surface should be optically plane and it should be able to reflect most of the light. Mirrors are designed to ensure it. And depending on the shapes, we may have plane mirrors, we use it in our houses, and we may have cylindrical mirrors also, we may have spherical mirrors also. Cylindrical mirrors are when you have a cylinder like this, so this type of surface, we call it cylindrical because it is curved only in this particular direction, not like this. Here it is a straight line. But for a sphere, it curves equally in all directions, right? So we may have cylindrical mirrors, we may even have spherical mirrors. Spherical mirrors are part of the sphere. So this is a sphere, and if I take only a part of it, say this much, and then depending on which surface is used to reflect, we will call it concave or convex. Okay. So if we are using this bulging side to reflect light, if we use it, this is convex. And this one is concave mirror. We are using this side to reflect light. Convex mirror, concave mirror, both of them, they are spherical mirrors because they are the part of the sphere. And this is a plane mirror. Okay. Now, laws of reflection, you know laws of reflection, you are aware of it. But even then, quickly we can revise. This is incident ray, this is reflected ray, and I can draw a perpendicular here, this will be normal. This angle is the angle of incidence and this one is the angle of reflection. Okay. First law says that the angle of incidence and angle of reflection, they are equal. Angle of incidence equals the angle of reflection, the first law of reflection. And the second one says that the incident ray, reflected ray and the normal, they all lie always in the same plane. Same plane means if I take the incident ray in this plane, this board, I draw a normal like this, then reflected ray will also be in this plane only. It won't come out. It can't be like this or go here. It will remain, it will be confined to this board only. If I am taking this plane, the incident ray, reflected ray can also be drawn in the same plane. So first law, angle of incidence equals the angle of reflection, and the second one, the incident ray, normal, and the reflected ray, they all lie in the same plane. Okay, these laws are valid for all types of mirrors, whether we are using cylindrical or we are using convex or concave. We can draw here also. Okay. If I take a ray like this, and here a light ray like this, how will we draw a normal on a curved surface? On any sphere, if I have to draw a normal at any point, draw a tangent and then take perpendicular to it. It will be the radius. Okay, radius is perpendicular to tangents drawn at any point on the surface. So if this is the center of the sphere of which this mirror is a part, we can draw a normal from here. So this is a normal here. So this is the angle of incidence, and then this ray will go somewhere here. This is reflection. And here also, this is the normal. Okay, and then the light will come something like this. So this is angle of incidence, this will be the angle of reflection. Okay, so this law for convex mirror, for a concave mirror, it is valid for all. Okay, now I told you about the laws of reflection. Now we can discuss few definitions related to spherical mirrors that we will be using. I will draw both the mirrors, concave and convex. Let this be the center of that sphere of which this mirror is a part. This is called center of curvature. Center of curvature. Center of that sphere of which the mirror is a part. Okay, and this is, what is this? This is the radius. So we will call it the radius of curvature. Radius of that sphere of which the mirror is a part. Okay, and then this point, we denote it by P. This is pole. So we can say the center of this part, center of that part of the mirror, that sphere which we are using as mirror. This, right? So center of this mirror, pole. And this line, we call it principal axis. This is principal axis. So we can say a line connecting pole and center of curvature, or a line passing through pole and center of curvature, that can be called the principal axis for this mirror. Okay, and if I take a parallel ray parallel to the principal axis, what will happen? This is normal. This is the angle of incidence, so it will pass from a point which we define as focus, and here also this is normal. This is I and this is R. So this is focus. So how can we define it? Try it yourself. A point on the principal axis at which the rays initially parallel to the principal axis pass after reflection from the mirror. A point on the principal axis, from which a ray initially parallel to the principal axis pass after reflection from the mirror. For concave. For convex, how will we define it? A point on the principal axis from which a ray initially parallel to the principal axis appear to come. See the difference. Here the point from which the ray passes after reflection, here the point from which the ray appears to come. So this is focus, and this such type of points or such type of images, we'll see it, we will call them virtual points or virtual images. So this is virtual point here. This is the real point from where the ray is actually passing, and this, the rays are actually appearing to come from that point. So we call it, this is virtual point. Okay, and then another definition related to this is focal length. Focal length is this distance, FP. So distance between pole and focus. Distance between pole and focus, this is called focal length. Okay, so center of curvature, radius of curvature, pole, principal axis, and focus, focal length. We can find the relation between this distance and this distance. This is R, and I can even call it I. I is equal to R. let us name these points P, N, and if this angle is I, then this is also I, right? And this total is 2I. So this is, see, this is 2I, so this will also be 2I. And this point N and P, they are very close, and one very important point that you are supposed to keep in mind, in this topic we shall be talking about paraxial rays. Paraxial rays are those which are very close to the axis. So all these expressions will be valid for paraxial rays only. So for paraxial rays, this point will be very close to it. So NP will be almost 0. So everywhere, wherever we write this distance, we will take it 0. So this point and this point, they will be taken as same. So how can I write 10I? 10I is Mn upon Cn, and 10-2I will be Mn upon Fn, this distance C. One this triangle and one this triangle. Okay. Now, if these angles are very small, if you are taking paraxial rays, it means M will also be very close to the principal axis. So in that case, these angles will be very small, and 10I will be taken as I, and 10-2I will be taken as 2I. 10-0 is 0. For very small angles, tan theta is theta. Sin theta is taken as theta. What about cos theta? For very small angles, cos theta is taken as 1. Okay. So this is I, this is 2I. Divide them. Mn upon Cn, Mn upon Fn is equal to 1 by 2. So 2 Fn is Cn. 2F is equal to R. Fn is focal length and Cn is radius of curvature. So focal length of a mirror depends only on radius of curvature. We will see in the next topic that focal length of a lens depends on many other factors also, not just on radii of curvatures. But for a spherical mirror, the focal length is half of the radius of curvature. Okay, that's enough for this class. In next class, we will take image formation. I will tell you about the sign conventions, image formation, and we will derive mirror formula.